Okay, thank you. So I'm WilliamTu. So today I'm going to talk about offloading the OVS flow processing using eBPF. So we already have two great talks about the eBPF, thanks to Thomas and thanks to Nick. So let me quickly go through what is BPF again. So actually you can think of BPF as just writing a restricted C program, and you could run it inside a Linux kernel. The difference is that compared to writing a Linux kernel module, which exposed to you so many Linux kernel data structure and could potentially introduce a bug or crash the Linux kernel, writing an eBPF program is safe. So this is because that there's a virtual eBPF virtual machine running inside the Linux kernel, and before you load your eBPF program into the kernel, you need to first pass the eBPF verifier. And this verifier will guarantee that your program will, in the end, terminate, and it won't crash, and it won't bring down your system. So there's safety guarantee in the BPF program. It also has maps and helper functions. So maps are just key value stored inside the Linux kernel, which allows you to share the data between different eBPF programs and your user space and eBPF program running inside the kernel. It also provides several helper functions for your eBPF program to interact with the other part of the Linux kernel. For example, if you want to modify the packet headers or you want to do push VLAN, you need to go through these helper functions and let Linux kernel do it for you. So with all these cool features of eBPF, we start to think about how does OVS could benefit from these eBPF models. So first is about the extensibility. So when we are introducing a new features to the OVS data path, once we finish implementation, we need to go through all the upstream process. The upstream process gives us a valuable feedbacks, but however, the time to upstream could be unpredictable. And once this data path feature get into the upstream, we also need to maintain the API compatibility, which means that we need to make sure different OVS version and different kernel version modules works correctly. And after that, we have maintenance costs and compatibility efforts. So Linux kernel keep changing, and new feature get add and new protocols it keep adding. So API might change, and we need to, with this new feature, we need to ensure that our new feature indeed work correctly with the newer version of the kernel. Sometimes we even need to backport this new feature into the older version. So there are bugs in this compatibility code, and usually it's pretty hard to find and hard to fix. So we hope that with this eBPF model, in the future, we could implement all the data path functionality using eBPF program. And in the hope that as long as kernel support eBPF virtual machine, we could load OVS kernel OVS data path, this eBPF program into it, and reduce the dependency and compatibility issue on different kernel versions. So this slide goes through a review of, if you are not so familiar with OVS data path, this goes through a review. So right now, we get a packet from the NICAR, and then it goes to driver. Right now, OVS kernel data path will get the packet from bridgehook, and we basically do parsing. We extract the flow key from the packet header. We do a lookup, and depending on the lookup result, we do different actions. For example, you could do MPLS push, and then you could output to a port, or you can drop. So there are a couple of ways to do eBPF in OVS. So first thing is we can write eBPF program in a parser or in the lookup path. And previously we have this approach like implementing this eBPF in the action stage. So we still remain the OVS kernel data path module, and instead then we add the a new BPF hook point to the action processing stage. This has a benefit of that when we want to implement a new data path actions or fix a bug, we could write a eBPF program and directly load it into the kernel module. However, this has limitations. For example, new protocol keeps coming, and sometimes people want to match new fields in our parsing stage. So working only on the eBPF action part isn't good enough. So in work, we are trying to do writing the whole entire OVS data path using eBPF program. There's a little bit change when we get the packet. Right now, after the driver, we get the packet from TC hook. So TC stands for traffic classification. It is a Linux packet queuing subsystem allowing you to usually do quads and traffic shaping, policing, etc. It also provides a very good eBPF hook point with a set of helper functions for us to modify the packet or to forward the packet and do all the modification we need. And then we go through eBPF parser, lookup, and actions. Then we also introduce a couple of eBPF maps. So these maps allow us to communicate between our eBPF program running inside the kernel and the OVS vSwitch in the user space. Then the next couple of slides, I'm going to dig more into the implementation part. So we'll talk about how to implement the header parsing and flow table lookup and action executions using eBPF. And finally, we'll show some performance number. So for the parsing, we start by writing our own parser code using eBPF. But then turn out it's a pretty standard process. So we take advantage of this P4 to eBPF compiler. So instead, we write an OVS P4 program which specify how do we want to parse the headers, the protocols. And then P4 to eBPF will generate the eBPF program for us. So it generates parser, which works through the protocol parsing graph, and it generates the parser, which we use at the last stage. When we have some packet modification, the deparser will write back to the packet. And you also generate maps for the flow lookup and counters. However, for OVS, we didn't take all the. So because one reason is that because OVS requires some Linux-specific metadata fields, so we need some change in the parser, and also we implement our own flow match and action part using our own eBPF program. So this is again a review of currently how OVS handle flow lookup in Linux kernel data paths. So a packet first comes into the parser, and then we will extract the flow key, and then we do a flow table lookup. This is in the Linux kernel. And then first packet will miss the table lookup, and it will miss opcode. So opcode will take this packet to the user space OVS vSwitch D. We done this through the nailing interface. And then OVS vSwitch D will do all the flow translation. It will look all the open flow tables, and then in the end, it will install a flow entries into the flow table. This is also through the nailing interface. And then, so the subsequent packet will hit the flow and then, it will hit the flow table and then execute the actions. So this is a fast path. So to do this logic in eBPF, we try to follow the same flow. So the packet comes to our eBPF parser, and then we look up in the flow table. Here we use eBPF hash map as our flow table. Then again, you will miss the flow table lookup, and then we have to do opcode. Here, because eBPF doesn't support nailing interface, but it supports perf ring buffer for the eBPF. So perf ring buffer is a mechanism for you to put the packet along with its metadata into the ring buffer, so that your user space program like OVS vSwitch could receive it and then it will do the same thing. Like it does flow translation, and in the end, it will install the flow into our tables. After the flow entry is installed, the subsequent packet will hit the table, the eBPF hash map, and it will execute the actions. So here, when we are installing the flow, we don't need to rely on netlink interface anymore, because user space program could use the BPF system call to directly program the eBPF hash map. In the beginning, we were trying to use this TLV interface, TLV format. However, there are some limitations in the BPF verifier right now, so we changed the TLV to fixed length. Basically, it's an array. So there's a extra benefit here, because right now we control, our OVS user space code control both the eBPF program we are going to load into the kernel and the user program itself. So basically, we can use any fixed binary format between the user space and kernel eBPF program. We don't need to consider different kernel data paths, whether it's compatible with our user space code or not. So after the lookup, then we have a list of actions to execute. So this is a review of how current OVS kernel data paths work. So if you want to do, for example, flooding, then it's, the data path action is just a list of port numbers. So port number, which means that you get the packet and then you forward it to port number 9, number 15, number 10, for example. If you want to do port mirroring and push a VLAN, then we have a data path action called set VLAN. And then we need to provide the metadata, for example, VLAN ID, and then you output to that port. If you want to do tunneling, then our user space will provide the metadata information for the tunnel. For example, what's the tunnel ID, what's the remote IP address. The data path action will execute this set tunnel and then output to a tunnel device. So to implement the same logic using eBPF, actually we encounter two major challenges. One, like Thomas mentioned before, eBPF program has limited instructions, so maximum 4K instruction size. So if we want to implement this idea of variable length of actions, one eBPF program might not be enough. Another challenge is that basically right now it's a for loop action. For loop, each loop will executing one data path actions at a time. So to implement this idea, actually, it's difficult because BPF verifier today disallow using for loop. Because once you use a for loop, the verifier couldn't guarantee that your program will terminate or not. So to resolve these two challenges, we first make each type of action an individual BPF program. So, which means that each action will have 4K instruction to implement. It turned out that each action is basically pretty small, and one eBPF program is good enough. And then at the end of each action, we need to tail call the next action to execute. So tail call is the mechanism for one BPF program to invoke another execution of a BPF program. So, however, to know at runtime what are the next action you should call into, we need to do an extra map lookup. So this map lookup will provide at one, for example, action 1 will look up, and then you will know that its next action is action 2. And moreover, we need some metadata for the action to execute. For example, if you want to push VLAN, you need to know the VLAN ID, and then we get this VLAN ID information from the map lookup. So there are some pros and cons of this approach. So first is that, of course, if we can implement all the action as individual eBPF program, eBPF program could be verified independently, and so it is good. Also, we could change the sequence of actions. Like sometimes we do rearrange it by based on frame flow result. So, but then, however, the overhead is that every time we pay an extra map lookup when we are executing this BPF actions. So putting all these things together by parsing, lookup, and action executions, we are able to do some performance evaluation. So we set up two machines. One is a sender, the other is OVS server, which receives the packet and do the forwarding. We have two 10-gig NIC card. One is, each one has dual port. So the sender keeps sending 64 byte, 14 million packets to the OVS server, and the OVS server will get the packet and forward it to another port. And we receive the packet at the sender side, the other port, to know what's the receiving packet rate per second. And we do this experiment using single flow and using single core on the OVS server and running with the latest Linux 4.9 RC3 kernel. So this is just a recap of the packet, how packet flows through our implementation. So first packet comes into the TC, and then we do parser, lookup, and different type of actions, the parser, depending on whether we change the packet or not, and then output to the TC egress. For the OVS data path, it's similar, but we don't have the deparser component, deparser stage. This shows the performance number of our eBPF data path action. First, we did a very simple experiment called redirect. So redirect doesn't do any parse, lookup, or action at all. So redirect is just a simple BPF program. Take one packet from one port and forward it to another port. So with that, we get about 1.9 million packets per second. So this is kind of the base BPF forwarding performance. Then we keep programming, we keep invoking parser, lookup actions and all the pipeline. First, we did hash action and push VLAN actions. Then we get numbers about 1.2 and 1.1. Then we found that actually hash, doing 5-tuple hash and push VLAN, our hardware actually, 10-gig NIC card actually offloaded this processing into their NIC card. So basically, these two actions doesn't do a lot. It just tell the NIC card to do offload it. So we lost about 0.9 million packets per second, which is due to the parser, lookup, and some of the overhead in actions and deparser. Then we continue doing actions like set MAC address. So sometimes people want to change the MAC address and forward. So we set MAC address, the performance goes down to 0.8. Then we did another experiment called set destination MAC, but without a deparser. Then it goes back to 1.1. So this means that actually at the deparser stage, when actions actually change the packet payload, the deparser will be invoked. If your action doesn't invoke any change, then deparser actually is a no-op. So here we can see that by verifying the set MAC without deparser, and we can see that the performance goes back to 1.1 million. Then we did a set GRE tunnel, which is about 0.4 million packets per second because for the tunnel, you need to go through another tunnel device and then output. So with the same environment, single core, single flow, we compare with the current OVS kernel data path actions. For simple outputting from one port to another port, we get about 1.3 million. And for the set destination MAC, we get about 1.2, and set retunnel, we get about 0.5. So the purpose here is not meant to show the raw performance of the OVS kernel data path or the raw performance of eBPF data path implementation. But it's also to understand that when we are designing and implementing this eBPF data path, we sort of knowing what are the performance overhead and what are the target for the optimization next. So here in this, you can see that deparser and parser might be a good target for our next optimization target. So in conclusion, this work shows the feasibility of implementing OVS data path entirely using eBPF program. So we hope that in the future, if we want to add new features into the OVS data path, it is as simple as writing a BPF program and load it into the different Linux kernel, as long as Linux kernel support the BPF virtual machine. And the idea is sort of to decouple the OVS Datapath functionality from the Linux kernel version so that we have less overhead of maintainability and compatibility efforts. Moreover, if in the future the Windows kernel or the Solaris kernel could support eBPF program, then we could directly run this eBPF datapath into different operating systems so that we could avoid maintaining different code in different operating systems. Finally, they are limited of eBPF, like Thomas mentioned, like not allowed to use for loop or instruction limitation, which might incur performance overhead. But I hope that as we keep implementing the features of OVS Datapath, we could identify more and share the result with the community. For the future work, we plan to complete all the OVS Datapath actions. For example, we are working on the connection tracking part. And also, right now, all the lookup in the eBPF Datapath are exact match cache. So we are planning to implement the mega flow lookup using eBPF map. Thank you.